right, so welcome back. Now we're going to look at the numerical solution strategies for the semiconductor equations. So we'll start out with the basic transport equations, then go into gridding and discretization and some overall approach on how to solve these expressions. All right, again, as a preface, these equations were derived in the previous lectures, and they are the industry standard even today. And they really help guide, understand the carrier transport in devices. These equations are in various degrees of sophistication and stability implemented in commercial tools. So there's no need as such, unless you really want to study how it works, to code up these differential expressions, because there's a lot of development of the state-of-the-art to solve those equations numerically that has evolved over literally the last 40 years. So you will most likely not code up a drift diffusion expression and a solution of the system, but you need to understand the methodologies and some of the shortcomings and some of the pitfalls that exist with these tools, such that you could become a power user of these tools and kind of detect when something goes haywire because the solution doesn't look quite right, and figure out what some of the limitations of your results might be. So the equations to be solved, again, Poisson equation gives you the band diagram, and drift diffusion, minority carrier transport, and ambipolar transport comes from these continuity equations for electrons and holes, and from drift and diffusion expressions for electrons and holes. Now, again, I had highlighted that briefly. There are conservation laws involved here that are universal. They're not specific to a particular problem. So if you look at these expressions, the Gauss's law in steady state and the current expressions in steady state are written down like this, where you lose the temporal dependencies, and this is how we write down typically the semiconductor equations in steady state. So they are these are the continuity expressions. Then there's some constitutive relationships with a specific problem at hand. They really reflect the particular physics of the problem. And this is here, for us, the way we discretize or solve the Poisson equation or the Gauss's law, where you have D is the dielectric constant of the materials times the electric field. So the displacement is the product of dielectric constants, and in our field in semiconductors we often call this a K or a kappa, not a epsilon like most physicists will use. And this corresponds to the negative gradient of electrostatic potential that we have in the device. Now, this is a specific way on how we write down these expressions for semiconductors and use them all the time. This is our nomenclature. Other fields would write down Gauss's law in different forms, but this is how we typically do it. Okay. The charge we consider in our system is another specific way for how we look at semiconductors. We divide out typically electrons and holes and donors and acceptors and account them as the charge in the system. So that is important for you to realize that there's other fields that might account for charges differently. If you do, for example, density functional theory, you count for electrons differently in a quantum way. But the fundamental continuity law, etc., still would persist. Now, the drift and diffusion equations really are very specific to the way we look at transport and in semiconductors. Remember, we had written those down earlier, always under the assumption that there's lots of scattering inside a specific domain. Without lots of scattering, the base assumption on the validity of these expressions would really be lost. So that's a pretty confining assumption to the system. And the way we treat generation and recombinations as functions of, say, electron density and hole density, etc., how they enter the continuity laws, these are also very specific to semiconductors. So what we have on the left is always true, but how we express these terms can be rather specific to the treatment in semiconductors. All right. So that being said, let's look at these semiconductor expressions. There are three coupled, nonlinear, second-order partial differential equations for the three unknowns that we have here, which is the charge, the potential, and we have two charges, electrons and holes. That's how we subdivided the system. So we have really three unknowns that are in three-dimensional space, and they're talking to each other. Again, I'm repeating here, the conservation laws are exact, but the transport equations, the distribution in this case, is somewhat approximate. Now the question is, why are these equations coupled? And how are they coupled, and so on? But you can think of it that way. If you started out from some potential landscape with a built-in electric field, you might have current that will flow. That current moves charges around. Those charges reflect back on Poisson expression, which changes the potential, and so on. So it's, in a sense, a circle that is of processes, of related processes, connected processes that balance out over time, if you will, if you want to think of it as a time-dependent problem. But the three expressions are really coupled. All right, so these are the basic transport expressions. Now let's talk about some gridding of these expressions. All right. So we typically in one dimensions would grid this out in some uniform grid that might be of lattice spacing A. And you represent your quantities, the potential, the electron density, and the hole density on that grid. There's a variety of ways of gridding. It doesn't have to be uniform boxes like shown here. They could be unequal. Certainly in three-dimensional systems, it's very common to use finite element methodologies where you have finite volumes, where you represent space such that you can have more complicated geometries with relatively few computational elements. So these computational boxes that contain charge might have different sizes, and they all have to be tied together in a meaningful way, as we had described before, that in and outflow through given surfaces for each of these little boxes needs to be meaningful and matched. All right, so here in this representation here, we're just going to consider equidistant, simple gridding, where we describe the variables on each point. And now the question remains, how do you build, for example, a differential, a first-order differential? So let's assume you have some continuous function f of x, and you want to discretize it on this uniform mesh with nodes separated by a. You can begin to expand this out in a Taylor-type form, where you express the f of x as its neighboring element and the differential, and you can pull this out and really have the differential be the difference between two nodes. So you can build the df/dx as a centered difference. So in a sense, you really know only the differential. Brings in some interesting conceptual questions if you don't have those values explicitly represented. This is the standard methodology in continuous uniform grids. The second order differential is represented in a form similar to what we have done for Schrödinger's equation. You Taylor expand out a point of the next lattice side by the neighboring lattice side with a second order differential, and you do this going left and you do this going right. You subtract or add these two expressions, you add them, and then you can build out the second order differential in this form where you look one atom or one side to the left, one side to the right, and you have two elements on side, and that's a second degree expansion for the second order differential. There's other, say, numerically more exact methodologies that rely on more neighbors. These are the simplest forms that are often adopted. So this is a 3-point formula, and if you needed more accuracy or you need derivatives in other directions or in to higher degrees, you will have to be more sophisticated on how you build these differentials. All right, so here are some gridding recipes and finite differences. It's very similar to what we had done with Schrödinger's equation. And we now step forward on looking how these equations, semiconductor equations, are discretized and what the boundary conditions in these systems might be. All right, so we have these three unknowns, potential, electron density, and hole density. And we need three equations for each of these nodes, at each node. And we discretize these properties in some what we would call a control volume. So this volume contains this node in a one-dimensional representation in this form. All right, so we have Poisson's equation, again stemming ultimately from Gauss's law. You represent the displacement field with a dielectric constant. In our field, we often give this a name kappa or K. You might have heard of high K dielectrics. That's where this nomenclature or this naming came from. And this then relates to the negative gradient of the electrostatic potential. All right, so we really have effectively turned Poisson's or Gauss's law into what we call Poisson's equation in semiconductors as a second order differential of the electrostatic potential as being minus the charge over the dielectric constant in the material. All right, so we discretize that over some control volume. This has the second order differential in it. For each site or in this volume, we have hole density minus the electron density plus donor density and minus the ionized acceptor density. All right, so we smooth out everything in these volumes. The notion of atoms, etc., is gone. Remember, in a sense, we have said that we want to make sure that in each of these bigger boxes, it makes sense to talk about drift and diffusion and scattering. So these tiny boxes here can't be too tiny to really make sense. All right, now we represent this expression here, Poisson expression. We just bring it all on one side, set it to 0, and we have an expression for the potential as a multivariate function of potentials at neighboring nodes, Vi minus 1, Vi plus 1, and on number of electrons and number of holes that can vary spatially on each site. Okay, so now we related these properties. Since V0 and V1 are known, one can use that for boundary conditions in the system. So that's what we use at the contacts, and we can iterate starting from the contacts in solutions of this problem. All right, let's assume that we have a potential that was found from some boundary conditions and imposing some charge density as a guess. Then we can do the next step to obtain new carrier concentrations. Okay, so somehow you either start from some guessed number of electrons, and you can now and boundary conditions, and that can give you a V throughout the device. Okay, let's assume you have your V known here, and you have some reasonable looking electron and hole distributions in the device. And then we'll talk about an iterative process on how you connect that. So now let's discretize the continuity equations. These are the expressions for current. So the electric field is the differential, the negative differential of the electrostatic potential. And we have a spatial variation of the electron density that we need to discretize, and that gets us in the continuity, the drift diffusion expression for the electrons. Okay, so in the simplest approach, you literally just discretize the first order differential, and as indicated here, Ni minus 1 plus Ni, the neighbors, divided by 1, potential as well. So here is the N that you need to discretize, and then the differential of the potential. And remember, we needed to find a solution that is on the neighboring sites to make sense. So you average out the N here in order to get the same balanced equation as for your differentials here, okay? Because they are on the neighboring sites sitting in between the grids, right? All right, so that's the simplest of approaches. There's other approaches that balance the neighbors in a different way, and there's advantages to it, but this is sort of the simplest approach. And also here, the drift diffusion expression for the electron density then can be set in this form, where you have a functional of these variables set to 0. So you do depend on the potential on neighboring sites, you do depend on the electron density on neighboring sites, and the hole density on neighboring sites. That's slightly different than the dependence we saw for the electrostatic potential. Now, we can do the same thing for the holes, of course, and we have these three expressions. And what we're after now is that we want to compute three unknowns at each node. We have these n nodes, and we have three unknowns and three n equations that are coupled to each other. All right, so let's consider, for example, again, the potential here, where we started out from. This potential relates neighboring nodes in terms of its potential and is on-site or diagonal in terms of the charges on that matrix. So we are representing this expression here of this functional that we had written down as AV equals some B, and V is the solution vector of the system that we want to impose or compute. We want to compute these n unknowns, and we represent this expression by a matrix that is typically in this form as written down in one dimension. It's tridiagonal, and it has some boundary conditions at the edges. Okay, so you end up with a tridiagonal expression. Tridiagonal because each neighboring node is related to each other. So if you want to be explicit, like on the second row, V1 must relate to V2, must relate to V3. And as you multiply this out, this must be a tridiagonal matrix. All right, so that kind of makes sense, I hope. At the end, again, you can need to impose some boundary conditions. And these boundary conditions are existent on the edges of this one-dimensional system. And typically what we assume here is that these boundaries are in some detailed balance. They are in equilibrium imposed by, say, a metal contact or otherwise. And that means the law of mass action applies, and we can figure out what the electron density should be given a doping concentration, etc., on these edges. Okay, so we can do this for both of these edges, and we can get the given that we have, say, a dopant density, we can figure out from the mass action law what the electron densities are. All right. If you had unequal materials on the two contact side or two different temperatures, you have to be careful what you consider the correct intrinsic concentration and related to the material. So just be careful what you do. These are sometimes important aspects to consider. So we discretize these expressions. Now let's look at a strategy on how you might solve them and how typically these tools that you might purchase solve them. It's an iterative approach, and it looks like this. You really have these three expressions, three equations on a grid of n nodes. And each of these three classes of unknowns, electrons, holes, and potential, are now thrown together in one big vector. Now, you might have boundary conditions here. On the right, you might have boundary conditions on the right for the holes, and you might have some boundary conditions also on the potential. Now, you solve the elements for electrons and holes on this block here. So that's really the continuity expression for the electrons. And you do the same for the holes here. So these relate to the center block, as chosen here. And the potential is on the bottom right block. Okay, so, but how are these blocks coupled, right? So in principle, if they weren't coupled, you could solve these three independently, but they are coupled. So let's look at this. So if you take the relationship between these elements n here and the potential here, you can see that the electrons in the system ultimately affect the charges that are entering what was just normally Poisson's equation. Now, the Poisson equation is modifying also the charge distribution in the system, which is governed by the continuity expression. The same is true for the holes, where the holes out of the continuity expression influence the overall charge in the Poisson expression. And similarly, the Poisson potential influences via the continuity expressions the holes that are in the continuity for the holes. All right, so the cross terms couple the Poisson expression to the continuity expressions. But there's more couplings from generation and recombination, typically here with recombination, where these continuity expressions for holes and electrons are coupled, since if you create an electron, you typically also then create or destroy a hole. All right, so these two are coupled as well. So you end up with a system of coupled nonlinear expressions. And those can be pretty painful to solve. If you could solve them explicitly here, you would do that. You would have to have numerical strategies. There's a whole art of devising what constitutes good convergence on these coupled expressions. A typical approach that is being done is that what you do is you might guess a potential landscape in a structure. You guess what the charge distributions would be. And often, if you look at simulation tools, you will start from from the equilibrium condition. So that is something that can be calculated relatively easily, and it's very stable to be computed. And this could enter the system into Poisson equation, and maybe then you begin to apply a slightly different voltage to the system, like from bias, etc. And given the bias change, you can then solve the electron distribution in the system that is modified, say, from the equilibrium condition, and you solve for the holes, and then you close the loop and you repeat until you're satisfied. So this is a very typical iterative approach on solving these three sets of equations. As I said, there's multiple strategies that are out there. There's a whole set of books, art forms, if you will, to be pursued. The point here I would like you to realize is that the solution of the numerical approaches are complex. You should understand that a solver, a tool may or may not converge under certain conditions. You need to understand some of the assumptions that are built in, and you need to understand that typically these tools have an iterative approach to them. Okay, so there's two methods in summary. There's an analytical approach and a numerical approach. Certainly the analytical approach gives great insights, similar to what we've done with Schrödinger's equation. However, realistically large systems, you end up having to model those explicitly on a computer to have a higher degree of sophistication and accuracy against experiments. So numerical solutions are certainly more versatile. You begin with a set of equations and boundary conditions, and you discretize the system. We highlighted simple one-dimensional discretization here, and then you solve the system typically by iteration. So those are the strategies, and this is really the end of section 18 on the semiconductor equations. So I thank you.